Hello guys, and welcome to my lesson presentation on Module 4, Chapters 11 and 12. I've created a PowerPoint for us to go over some problems, and hopefully they'll be able to help you with your homework. Okay, let's present this. All right, so we're doing transformations, symmetries, tilings, and then Chapter 12 is congruence, constructions, and similarities. Okay, so our first problem, there's Ephraim and Devontae. We're given a pattern block figure and asked to reflect the figure over the horizontal line through the center of the squares. So here's the figure they're given. Now this gray line right here is the horizontal line that they're supposed to reflect over. Well, Ephraim and Devontae came up with this figure. Now if you look at it, here's our line of symmetry. So we're supposed to reflect it over this. And the figure that they've came up with, they rearranged their blocks, they actually rotated their figure 180 degrees. So we need to fix it for them and show them how they messed up. So when you reflect something, think about when you're looking in a mirror, you're seeing a reflection. So it's just an image of you, it's just a little different. So here's the reflection of the pattern block figure that they were supposed to have done. If you notice, the purple shape is on the top of the picture, and then the two green triangles at the bottom. They came up with something similar that Ephraim and Devontae did, but the only thing different was these two triangles at the bottom, they're pointed a different direction. So if they would have just flipped it a little bit, they would have came up with the correct answer. All right, so our next problem, we are going to do line of symmetry. We're going to identify things. Well, I made it kind of simple. I mean, I gave you guys examples of each, and we're going to, so the first thing they want us to do is the one line of symmetry, but no rotational symmetry. So for that one, maybe I should do some definitions first. Let's do that. So the line of symmetry is just an imaginary line where you can fold the image in half, and both halves are exactly the same. So the line of symmetry and reflection symmetry from definitions from the book are saying they're pretty much the same thing, because when reflection symmetry, remember, if you're looking in a mirror, reflection, right? So rotational symmetry is different. It's where a figure is superimposed onto itself, on itself, when it is rotated through a certain angle between 0 degrees and 360 degrees. So for the first one, it wants one line of symmetry, but no rotational symmetry. So I gave you guys an isosceles triangle. This has one line of symmetry, but no rotational. So here's our line of symmetry. You can see you can fold it in half, and both halves are exactly the same. So for rotational symmetry, but no reflection symmetry, I actually went with the parallelogram. If you were to fold the parallelogram in half, it wouldn't be exactly the same. So there's no reflection symmetry. Rotational symmetry, it has. Okay, so for the one line of symmetry and rotational symmetry, that is not possible. Okay, so for our next one, for this one, it says Myra cut out a regular pentagon, a hexagon, and an octagon. And to her, it looks like they form a vertex figure. But we need to see if it does, and if it doesn't, explain why. So the vertex figure is an arrangement of non-overlapping polygonal tiles surrounding a common vertex. So in our picture, the common vertex will be right here, where all three of the shapes come together. Now, the measures of the interior angles meeting at the vertex figure must add up to 360 degrees. You're probably thinking, well, how do we know if that happens, and how do we figure that out? Well, I think you'll remember from past lessons how to find the interior angles of a polygon. We use this formula. So remember, n is the number of sides of the polygon. So to do that, let's pull out here's our pentagon. So we're going to plug that into our formula. So 5 minus 2 times 180 divided by 5, which will give us 108 degrees. So the interior angles of this pentagon is 108 degrees. Now for our octagon, I'm sorry. Okay, so for our octagon, we use the same formula. Not octagon, or hexagon, I'm sorry, we're not on the octagon yet. hexagon, 6 minus 2 times 180 divided by 6 is going to give us 120. Now for the octagon, we do the same thing. 8 minus 2 times 180 divided by 8 is going to give us 135 degrees. Now to figure out if these is a vertex figure, remember, they have to equal 360 degrees. So when we add 108, 120, and 135, we actually get 363 degrees, which means it's not a vertex figure because they're overlapping just a little bit. Okay, let's move on to our next one. So this one, you're probably thinking, what is this? Okay, so we have this wonderful figure. Okay, so we have line M, which is this purple one. Then we have line P. Okay, and then there's Q and S right here with the arc. Okay, and there's point V and T down here at the bottom. Now they're going to want us to, I don't know if you'd say answer questions or demonstrate. Let's say demonstrate if certain things are true, and if so, then how are they true? Okay, so the first thing they want us to figure out is triangle QPT congruent to triangle SPT? Okay. Okay, let's use my little highlighter here. Oh, we're not ready for you yet. Okay, so our triangle. So we're going to do Q, P, T. So this whole thing right here, right? Let's color it in a little bit. Okay, my bad. This triangle is congruent to this one, SPT. Okay, y'all are getting the drift, right? So messy. Okay, and this statement is true for the simple fact that if you see this line PT that goes straight down, this dark blue one that I've messed up, is congruent to itself. And these two green lines are congruent to each other, and the pink lines are congruent to each other. So, so since PT is congruent to itself, and the green lines are congruent to each other, and the pink lines are congruent to each other, it satisfies the S property, which is side, side, side property. Okay, so our next one is I want to know if angle QPT is congruent to angle SPT. So let's see. Maybe change our color on that point, on that thing. So maybe we can see it better. Let's go with this dark gray. Okay, so QPT, so QPT goes all the way down, and then SPT. Okay, now this is a true statement. Angle QPT is congruent to angle SPT. Again, they are corresponding angles. You can see right here, they're together, they're side by side, which can correspond. They're corresponding, and they share PV, which is congruent to itself, just like before. So the angles are corresponding, and these triangles are congruent. So the statement is true. Okay, so our next one they want us to do is triangle QPV is congruent to triangle SPV. So QPV, right here, this triangle, and SPV. I'll just make one big triangle. How about that? So QP, I'll cut it down, SPV, and these are triangles, so they're connected right here. Okay, so this statement is true again. I went ahead on the last one, sorry. PV, right here, this line that goes, separates the two triangles, is congruent to itself. And these two sides are congruent to each other. So that's going to satisfy the SAS property, which is side angle side. Okay, let's get rid of all that messiness. The next thing they want us to do is QVP, angle QVP. Is it a right angle? So let's look. Q, B, and then P. They want to know if right here, if that is a right angle. Well, this statement is true again, because QVP and SVP, so right here, SVP, are adjacent, and if you remember from our lessons in the past, they are supplementary angles. So when you have a supplementary angle, they equal 180 degrees. Since we have two of them, that means QVP has to be right angle, which equals 90 degrees. All right. Hopefully my messiness didn't mess y'all up. Let's go to the next one. Okay, so on this one, we are given a whole mess of stuff. So the first thing it wants us to do is draw a regular pentagon labeled penta, P-E-N-T-A, which there's our beautiful pentagon. Now it's wanting us to do an equilateral triangle labeled PQR. And if you notice, we already have a P right here, so they're going to share a point. So there's our equilateral triangle PQR. Now they're wanting us to inscribe penta and PQR, our pentagon and our triangle. And if you remember from our lesson, I believe it was just our last module, when you inscribe something, it's going to be inside. So we're going to have a circle around our shapes because our shapes are going to be inscribed or inside of that circle. And here we go. So they're inscribed now. Now it wants us to figure out what this angle equals. So they want a measurement of angle NOQ. Okay, to figure this out, we're going to use something called the angle bisectors. This is the one it took me a minute to figure it out, but yeah, it's pretty simple. So you have a pentagon, which is 5 sides, right? 5 pentagon. Okay, when you do the bisectors, it actually produces an inscribed decagon. And then you have an equilateral triangle that's inscribed in our circle. And the triangle's 3 sides, but when you do the angle bisectors, it gives you a hexagon, which is 6 sides. When you add 10 plus 6, you're going to get 16. But if you remember what I said, they share this pretty little point right here, P, so that's technically 15. So you get this pretty little thing, big old pie sliced up. So here's our angle NOQ that they want us to find. And if you remember, a circle is going to equal 360 degrees. So to find out what the angle of NOQ is, we're going to divide it by our 15 bisectors. So we get 360 divided by 15, which gives us 24 degrees. So angle NOQ is 24 degrees. All right, let's move on to our next one. All right, here we go. So this one, if you see our picture right here, this is Jenny. All right, so Jenny is holding her ruler 2 feet in front of her eyes. Right here, you see there's the ruler. It's this little mark right there. She sees the top and the bottom points of the vertical cliff. And they line up with marks separated on her ruler by 1.5 inches. So Jenny is about 1/4 mile away from the cliff. And they want to know what is the approximate height of the cliff. And remember that a mile is 5,280 feet. The first thing we're going to talk about is similar triangles. Okay, now two figures are similar if they have the same shape, but they don't have to be the same size. And I'm fixing to show you. So this green dashed triangle is similar to this little green triangle that I just inserted. Those are similar triangles, but if you notice the size difference, the green dashed one is way bigger than this little bitty old green triangle. All right, so we need to figure out what the height of the cliff is. Now to do that, I have worked a formula up for us. We're going to do the distance from her eyes to the ruler over the distance between ruler markings is going to equal her distance from the cliff and the height of the cliff. So let's plug in what we know. So we don't know the height of the cliff, but we know that she was a 1/4 mile from the cliff. And then we know that the distance between the ruler markings was 1.5 inches. And we know that the ruler was 2 feet from her eyes. All right, in order to solve this, we're going to have to convert our measurements into the same deal. So we can't have a mile, inches, and feet. Let's all make it into feet. So to figure that out, we need to know there's, for 1/4 mile, that's actually 1,320 feet. 1.5 inches is 0.125 feet, and then 2 feet. Now, to solve this, we need the height of the cliff by itself. So we're going to multiply 1320 to both sides. So now we have 0.125 feet times 1,320 feet divided by 2 feet. And to get the answer of the height of the cliff, we work our problem and we get 82.5 feet. All right, guys, so that's all I have for our lesson. I hope it's helped you with your homework. And